Hello and welcome to the new session. Uh, in the previous session, we talked about bifurcation, especially Hopf bifurcation. And so after introducing R and theta as the amplitude and the phase of the system. So we were talking about some equations that were based on R and theta, but for solving those equations, you need some algorithms like Euler method. So you can do that, solve those equations by, for instance, those Python programming uh, in your system. But there's another way. Another way is taking a gift from Stuart Heitman. He wrote a very simple code based on BD Toolbox, Brain Dynamic Toolbox, which is interesting. It's for visualizing Hopf bifurcation. So so it's like a MATLAB code here, for instance, Hopf xy.m. You can add that to the models here. For instance, you have in BD Toolkit, there's a folder named models, and you can add this one to these models and add the path. And after that, you can just type help Hopf xy or whatever the name is and load it. So it's interesting to know that you can actually also solve your differential equations and getting the visualized form of it by the help of this interesting toolbox. And we can now just see how it works, right? So he actually came with you can start like a function like the name of the system, which you can call it Hope xy. And so the system is going to use this ODE function solver. And this is just for like, it's very simple, right? So your system, it's the definition of its parameters are like this, the name of it and the value of it and the limit of it, like the range of it. You can change it as well, right? You can, like, for instance, put it like -2 until 2. And the variation, the definition of your variation as well. You can also see that you can just name it like x and y and the limit of it. This is the structure of your program. After creating the structure, you can use this BD GUI for visualizing it. So this is just for representation of your equations in the LaTeX format, which kind of you can use it like just for seeing the equations. And then you just use the Brain Dynamic Toolbox, which has already written by Stuart Heitman. Here you can, for instance, use time portrait, you can use phase portrait, you can use solver panel, and these are just creation of the panels that you need in your visualizing window. And the time span, which can this is a good assumption. And the ODE solver, it can be, for instance, this Euler method. And these are the time steps and initial steps. That's all. This much simple you can actually write on based on this toolbox and write your code to solve your equations and make uh, the the comprehensive understanding of the behavior of the system that you are interested in. So, and this is the ODE function that you are seeking to solve, which you have one dx and one dy, and we actually so you have a parameter like alpha or a in our lecture we talked about, and you are going to calculate y. So this is just the initial conditions, and this is the normal form of Hope bifurcation, which actually we talked and we actually added some extra terms to this, but uh, it's just the normal form, and that's all. After writing this code, or you can I will also upload this and you can use it as well. I think uh, he doesn't have any problem with this. Indeed, I think it's gonna be nice if some of you also are interested in developing these packages as well, right? By by cooperating in this MATLAB code, and we can also use it for the evaluation process at this semester. So you just again come with this system which is Hope XY, which first you just named it, and then you just visualize it. That's all, right? After that. After that, you will have maybe I can. Yeah, after that, you can see that here, for instance, in the if I choose bifurcation diagram here, and if I also make it 3D, it's very simple to use it, right? It's the good thing really about this. And if I also, so you see that when I change these ranges from, for instance, -2 to 2, the limit of my parameter, it is also changing here. And this is the initial condition. For the initial condition, I am going to use, for instance, 0.1, because if it is just 0 and 0, then it will just stay in that fixed point. So if I do this, and if I just clear the axis, and if I also wanna see it in this, so this is my initial condition, right? In this initial condition, by changing the parameter like alpha, which is the bifurcation parameter, you see that nothing is changing until the moment of bifurcation point, which is alpha equals to 0. And then this fixed point is, which actually, if I change now, I will talk about this. This fixed point here is going to be change and creation of a limit cycle. This is the birth of your limit cycle by changing this alpha, which if I calibrate the axis, if I want to so this is again your initial condition, right? This is a spiral which starts from do I have the marker? Yes. So if I want to see that how it goes, you see that this spiral is spiral out. There is an unstable limit unstable fixed point here, which this it absorbed to this limit cycle out of it. But if I change it, for instance, to, I don't know, if I change it to 10, for instance, then it is out of it. If I, again, no, 10 was a lot, maybe 3. Wait, actually, let me calibrate it. So if it is outside of this limit cycle, like here, then it is absorbing to this limit cycle. And when it is inside this limit cycle, like this one, it is also attracting to this limit cycle. So there's an unstable focus here, and there's like all of the trajectories out of this limit cycle, this stable limit cycle is attracting to this. So once again, just for because it's a beautiful shape, but I want to just change it to maybe maybe here I can change this to like maybe 0 point, I don't know, like 5 maybe. And you can see that it starts from here, and maybe I should make it more, maybe even Y, like I don't know, like 1. So I am still seeking for a better value. Yeah. Oh, so here, I don't know, maybe 10, 10. Maybe I can calibrate it. Yeah, from wherever it is, it just absorbed to this, right? And if I want to, I want you to actually see the spiral. That's why I am insisting on this. 0.2 maybe. 0.4 if I can calibrate it, and if I clear it, and if I calibrate it, then you see that it is actually anyway. Yeah, by changing these parameters, you can see that you can go get closer, like maybe this. Yeah, by the way, it starts from here, and always it just absorbed to this. So this alpha starts from -2 to 2. The bifurcation point is this 0. So if I want to see it better from this view, for instance, and if I, instead of this initial condition, if I change it to, for instance, 1, and this one to 0, then you see that by the changing of this alpha, this spiral at the time of 0, if I want to see it like this is my alpha, right? At 0 you will see that there is a big change, right? So you see that this fixed point at the choice of 0 for alpha became to be a limit cycle. This is actually a stable focus here, and then it turns out to be an unstable focus inside the limit cycle, and all of the trajectories outside of this uh, the limit cycle are attracting to this limit cycle, right? So if I just want to calibrate it for a better view, it's something like this. It's a beautiful point, right? This is the birth of Hopf bifurcation. So if some of you are interested to work and kind of developing uh, these kinds of work, like developing these packages or working based on this brain dynamic toolbox, it's also available. It's possible to work for your evaluation process. Okay, now we have the idea that what limit cycle is. So with this limit cycle as the attractor of our dynamical systems, which is showing actually the spiking behavior, the tonic spiking, the periodic spiking, we want to actually introduce a concept named synchronization, which is freely available on the yizikevich.com, the website, and now, so the idea is that until now we were talking about spiking of one single neuron, but now we want to, like in general, we are looking at brain as a network of spiking neurons. Okay, we also have some other materials there, but for now we assume that the information are going to be transmitted by the spiking neurons, and by the networks of tonically spiking neurons, we say that actually synchronization also exists in nature, like everywhere you can find synchrony, because it is coming from the oscillation and the phase of the oscillations in the network of oscillators. So brain is not also a special thing. Well, it is a special thing, but the whole science and breaking these idols is like believing that it is possible to know and understand even some complex systems like brain, which we already in some levels we know how brain works, right? So neurons can synchronize and exhibit collective behavior that is not intrinsic to any individual neuron. It means that actually this collective behavior, like there is this idea in complex system that actually the set of the elements have, because of the interaction between them, it has some properties that is not possible just by summation of those elements. It has something else that the whole of the system, it exhibits something new, some new phenomena that we called like collective behavior. And synchrony is has this idea that actually they are going to be co-activated. For instance, if a neuron and another neuron 1 and neuron 2 are co-activated, then there is something between them. Then the time of their interaction is decreased, and so neurons that fire together wire together, right? And for instance, you can then say that the synapses, because of the synaptic plasticity between them, there is a kind of channel between them, and those channel, those synaptic connections between them are going to be strengthened, or it it can be even going to be weak. If they are not firing together, it's going to be weak uh, during the time. So synchrony, you can see the synchronization and the, for instance, partial synchrony in the generation of alpha or gamma EEG rhythms. Maybe some of you are interested in the experimental works which already you can find in the lab, in neuroinformatic labs, and also you can say, for instance, about epilepsy, right? Because a healthy brain is a noisy brain. You cannot see any kind of pattern in a healthy brain. It's But when all of these neurons are spiking together, then there's a complete order. Then you can see epilepsy, and it's not a healthy brain. It doesn't mean that synchrony is always good, but synchrony can exhibit some collective behavior. That's the important thing. Sometimes it's good, sometimes it's bad. There is no intrinsic goodness and badness, maybe. By the way, there is an ongoing debate also on the role of synchrony in neural computations. You can take, for instance, binding problems, which I am also working in the lab on that. Some aspect of orientation selectivity generation in the grid of networks of neurons. So I mean, there are some ideas that actually, binding problem, you can say that you are looking at these words, right? You are seeing BINDING, and the way that you can combine them together and bind them together, and making a word, or combining these words together and making a sentence, and generating a meaning, it's a binding problem. Or you can say that in visual cortex, colors of the objects are being recognized in some regions of the brain, and the position and orientation and the object itself are going to be recognized detected in another region of the brain. And the way that you can combine them together and say that this line, for instance, is purple, right? This kind of thinking is some examples of binding problem. And so the goal is that, so we want to talk about networks, right? Networks of neurons are consisted of a bunch of neurons, right? So the first thing is the interaction, or looking at the interaction between neuron 1 and neuron 2. If you know the interaction between neuron 1 and neuron 2, then you can extend it to the networks of neurons, like a million number of neurons, maybe. And and the limit cycle, which we were talking about, is actually important in showing the spiking behavior. So the type of the bifurcation of limit cycle attractor generating tonic spiking. The way that how to use the phase models to understand the collective behavior of many coupled oscillations. Oscillators are like the goal of this approach. So in this chapter we actually Yeah, there are several forms of couplings. For instance, one of them is pulsed coupling, like weak coupling and stuff. But in this chapter, we just want to have a general idea, and if somebody is interested in, then he or she can excavate it more and more. So in this pulse coupling, we have this formulation in this function here, like x dot equal to f of x plus a delta t minus ts, which this delta, don't think about it. This delta is something like this delta function of t minus t. This is like you can say that it's like a Dirac function, that you don't need to actually know about it. Just know that if t is equal to ts, then delta t minus ts is equal to 1, and if t is not equal to ts, then this delta is equal to 0. That's all. So it just tries to say that at the time of the spiking neuron, then there is this a here, which is going to be used for that resetting. So having this equation, actually, which still have this main part, which we have it in our dynamical systems. You can use it for V, right? For membrane potential, for instance. And it has an exponential limit, stable limit cycles, which exhibits the tonic spiking and experiencing pulsed stimulation at time s. So if the time is equal to ts, then you have this spiking, and then it is going to be resetted to its initial state. That instantly increases the state variable by constant a. And so for the phase, we say that phase is actually, so we are going to actually we want to talk about this picture here, this figure 10.1, and the phase is usually taken to be the limit, is usually to be taken to be the time since the last spike. Since the last spike. Here, for instance, you can say we've seen in the phase portrait, right? So we have this t as our period, and we talk about it, that what period is, and this 2t is the is equal to 2 times t, and so on. And so this is your period, right? This is the period, and the phase that we are talking about here, the phase of the oscillation, is going to be governed by this t. So we have, for instance, if you take this like t, then if you say that theta is equal to t, then this theta, which is a function of t, which is equal to t itself, it's like this diagonal line over here. And after reaching this period of t, it is going to be resetted to the phase is going to be 0 again. So this is t, right? From 0 to t. And again it's going to be 0, and again it increased to t, and again it is resetting, and so on. Right? This is the understanding of actually oscillation, right? Because oscillation means that there is a period, and it comes, the state of the system comes back to its starting point, or starting state, and there's a periodic trajectory there. So It is completely like corresponding to this to this membrane potential here. You can see that here this phase of oscillation with each spiking, this is going to be resetted again. So all of them are coming from those simplifications idea. So we say that a function x is periodic if there is a constant. So it's important to be constant, right? If there is a constant like t, which is positive, such that again after the period of t, it is going to be itself again, like x of t plus t is equal to x of t. This is the definition of periodicity, right? The minimal value, it can be also like 2, right? It can be also 3, whatever. X t plus 3 times t also is equal to x of t. But the minimal value of it, of this constant, is the period. We call it period, this t, which is the minimal value. The periodic functions appear in dynamical systems having limit cycle attractors, which we were focusing on. Here I did something wrong. Okay, if the system has two or more coexisting limit cycles, so some of them are very simple probably for you. I just don't talk about these things because for instance the initial point is just the choice, but you can take it like the peak at the moment of a spiking, just for the sake of consistency. That's just the choice. And new, or it's just the name, right? Always denotes the phase of the oscillation, and t denotes the period of the oscillation, and that's all. But if the system has two or more coexistence limit cycles, limit cycle attractors, because it can also be unstable, but we are working with stable ones, then separate phase variables needs to define for each attractor, which it makes sense, right? So so here for instance we were talking about the flows on circle, right? The flows on circle, we introduced something named theta here, and you can see that here, like it's exactly the same right here, like from 0 to t, and it starts from 0 to t, right? This theta as the function as the phase of our system, and the t itself, like you can divide it to 8 parts, like t over 8, like t over 4, and so on. And so it is like it brings you like the idea that you can actually use this sine and cosine idea, right? Because it's like on a circle, and there is this theta here as the phase of your system, and you can kind of model and simulate your system with these functions, like triangulate functions like sine or cosine. And if we want to talk about membrane potentials in our system, like with like n the activation gate variable with respect to membrane potential, then you already seen that, well, probably you're bored of seeing this figure over here. Imagine how Professor Pipa feels. Maybe. So it starts from zero, like here, and like here it's the initial state, right? And you already seen that it's like if you do the discretization here, the points, like the state of the system is far away from each other, and it's moving the state of the system on this trajectory, which is the limit cycle, is moving fastly until reaching this t over 8, and then still it is kind of fast, but then it is going to be slowly and slowly and slowly, and this is the moment that you feel that ghost actually here. You can feel, you can see that there's a kind of ghost because it is like very close to that fixed point. That this is the V alkaline, right? This is the V alkaline, and by the current you can bring it down, and if they cross each other here, then you see that it's going to be a stable fixed point, and when now it doesn't exist, but the ghost still exists, and this is why it is very slow. But this limit cycle attractor here, this limit cycle is your tonic spiking behavior. So if it is just coming from so you have the equilibrium state like fixed point, and if it is excitable, then once it just spikes and come back to that fixed point. But if the parameter of the system changes, then its dynamic also will change, and it means that actually you will have limit cycles, and it means that tonic spiking. It means that you have several spikes after spikes, after spikes, which is the limit cycle, and the way that you can understand it is understanding this phase like theta or nu. That's another name, right? So now let's talk about isochrones. Isochrones is like this. Iso, we want to like attack binding in our mind. Iso means equal, and chron means time. So it means like equal times. So what it means, why we need it? We need it to understand the power of phase in our phase plane, the power of the essence and the meaning of phase. The phase of the oscillation can be also outside of the limit cycle, right? So for instance here we have, this is our limit cycle. This is our limit cycle here, and this is a point which is on this limit cycle. It is on this limit cycle. What about y here? What about another state, like another point like this here? How about this one? How about this one? How about all of these states of the system outside and inside of our limit cycle? So the idea is that this y, like here, this y0, if we just let the time goes, like if t goes to infinity, to positive infinity, then it means that actually At the end, this y of t1 after a period of time are going to be here, and it's going to be y of t2 and then y of t3, which is equal to x of t3. And then after reaching this limit cycle, because it is actually like an unstable like a trajectory that is coming out of this unstable limit fixed point here, and it absorbed to this limit cycle over here, right? And then always it is just repeating on this limit cycle. So the idea is that this y0 here, it's very, very, very dirty now. Let me do this. So this y0 here is corresponding to this x0 here, right? Y0 is corresponding to x0. And it means that the phase, like we say that there is something named nu, which is our phase. Phase of y is equal to phase of like the point of x, which both of them are a function of time, right? Like nu y of t is equal to nu of x of t. So after, when time goes to infinity, then this y and y, it doesn't matter actually, you start from here or here or here or here or here, all of them will be on this limit cycle. And for understanding this, we say that the phase of all of these points are same, they are equal. The phase that we talked about, like that theta in which is actually the time which is based on the period. So but we just call it like nu here, right? It's just a name. And this is the definition of isochron. So this is our isochron. All of these points on this isochron has the same phase, and all of them will be attracted to this limit cycle here, and they will all doing spiking. So this was that isochron that we were talking about here. And there are also, for instance, this isochron as well. It means that here, if I have here another, like for instance, take like z0, then it goes this trajectory to limit cycle. Here it's gonna be z1, which this one corresponds to this x0, and this z1 actually like at the time of z1, it's this x is here, and after all, like xzn will be equal to xn here. And when it is on the limit cycle, then it just goes around. So all of these phase plane here, it is full of isochrons. Just 40 of them are being shown here, like this, like this, like this. All of these points here, which are the representation of the state of our system, they have just the same phase. This is the idea of isochron. That's all. But for understanding it better, let's see what Izhikevich is telling us here. So this is the thing that I said, that when time goes to infinity, then x of t will be y of t will be x of t. And so alternatively, you can talk. So we were talking about y, we were trying to understand x, and now you can go vice versa. You can say for every x as the solution on limit cycle, we have an isochron. We have infinite numbers of states in our system that are fitted on that isochron of corresponding to x, and this is why he uses this alternatively. Alternatively, we consider a point on limit cycle x0 and find all the other points y0 that satisfy this. The set of all such points is called stable manifold of x0, or you can say isochron. The manifold represents solutions having equal phases. Every point on the plane except the unstable equilibrium, which is this one, except this one. All of the points here, they are on a limit, they are on an isochron, except unstable equilibrium gives rise a trajectory that approaches the limit cycle. Therefore, every point has some phase. Let nu denotes the phase of the point of x, like nu of x is the phase of point x. Then the entire plane is foliated by isochrons. All it is completely covered by isochrons. So there is this there is two conditions here. One of them is continuity, the other one is invariance. So you say that the function nu, which is our phase, it is continuous so that nearby points have nearby phases. So it means that here, 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 it is a continuous thing. All of them has the same phase outside and inside the limit cycle. And the other one is invariance. So if there is a point here, for instance, which its phase is equal to the point here, then in the long run, or if by the evolution this point, which is the representation of this state of the system, at any time t, for all t, nu of x of t is equal to nu of y of t. So if it is y, then it is x, and it is invariant. It always will stays. It doesn't vary. Isochrons are mapped to isochrons by flow of the vector field that we talked about. So we have a vector field here. If you maybe it's better to draw it like this, that we have a vector field like this, we have this, we have this, and here we have this, here we have this, here we have this. These are the things that the way that you can actually find the vector fields. And vector fields, for finding the vector fields, you can actually use those Jacobian matrix and eigenvalues and eigenvectors and so on. So this was the isochron, and you can see that, for instance, here in Hopf oscillator, you can see that it's very symmetric here, like this. This is the imaginary part of Z, this is the real part of Z, and there is these are the isochrones of this oscillator, for instance. The other one which we talked about was the Van der Pol oscillator, which we also used Brain Dynamic Toolbox for this. And you see that the isochrones are like this, and I can, for instance, if I tell you, for instance, what will happen if I have a state like y0, like here, this point, you can say that because its isochrone is it is corresponding to this x, then it's in phase with x, like nu of y0 is equal to nu of x0, like by time, like in t. So yeah, it's interesting, right? Because any point here inside and outside of the limit cycle, it is at the end it's going to be attracted to this limit cycle over here, and for understanding this, you just need to analyze the phase of that state. So if by phase model analysis, you can completely avoid of computing all of these states. You just need to understand limit cycles. It's interesting. You can also see that in the lectures by Professor Pippa, you have class 1 and class 2 neurons, and you can see that the dynamics of them will be different, because this null line here, there is this very close point here, and there is this intersection here, and here you can see that there is this intersection here, and all of them are having, like, again, both of them has this limit cycle, but you probably now know about the differences in the frequency, which one of them is this is class 2 and the other one is class 1, and it is this there is a big gap here for the frequency, and this is in class 2 neurons. And you can see that the isochrones are also different for them, and you can take a lot of information and out of the states, the states of the system that are in those regions of the phase plane of the system. So next topic will be PRC and synchronization, which I will cover it in the next video. Have a great time.